And let me introduce first what local efficiency of a particle is. Its intuition is very simple. The intuition is how many times the operator was used to generate interesting mutants. So for example, let's calculate the local efficiency of a particle with a 1-bit flip operator of the first swarms. And for simplicity, let's assume that it generates 10 mutants in total from the first swarms. And among them, there are 3 interesting mutants. In this situation, additionally, we assume that the number of sampled times for 1-bit flip operators is sampled 5 times from the first swarm. And out of the 5 times, it contributed to generating 2 interesting inputs. And then the local efficiency is calculated by as simply dividing the number of interesting mutants contributed by the operator into the total number of sample times of the operators. So in this case, the local efficiency of 1-bit operator will be 0.4 in this case. In this way, this learning algorithm first calculates the local efficiency of all the particles in all the swarms as follows. And intuitively, this local efficiency represents how much each mutation operator contributed to generating interesting input in each swarms. Second, the global efficiency literally denotes the efficiency of each operator when considering all swarms, not considering each swarms. So for example, suppose that 50 mutants are generated from all the 5 swarms in total. And among them, 20 mutants are interesting. In this situation, the number of interesting mutants contributed by 1-bit flip operator and the total sample time of the 1-bit flip operators are 10 and 20 respectively. Then using this same equation of the local efficiency, the global efficiency of this operator will be 0.5 in this case. And with this calculated local and the global efficiency of all the swarms and all the particles, and this learning algorithm updates each swarms. That is, it updates the probabilistic distribution of each swarm as well. So I will skip the part of applying this calculated local and global efficiency value to update the distributions, as it's straightforward to put them into the PSO update equations. And so as you can see in these pictures, this customized learning algorithm continuously repeat the process of generating mutants from the multiple swarms sequentially and updating swarms based on the accumulated data, such as interesting mutants, until the testing budget is over. And so if your research is also solving the problem of finding such an optimal distribution from the huge search space, it would be a good chance to apply this particle swarm optimization algorithm, I think. And they have conducted the experiment for 13 open source real world programs, where some benchmark programs such as OBJ-dump have more than 1 million lines of code. That is, they conduct very realistic. They used very realistic programs. And as a testing budget, 10 days were given. This is also very realistic settings. And in short, this program adaptive mutation strategy MOPT outperforms the program agnostic strategy AFL. As you can see, MOPT found about 3,000 unique crashes, but AFL managed to find about 600 crashes. In terms of unique execution paths, MOPT succeeded in discovering about twice as many paths as AFL. This is very surprising result to me. And I will also give a very brief introduction to CMFudge, a more recent work published this year in empirical software engineering journals. And actually, CMFudge shares the really similar motivation with MOPT. They tackled that this conventional program agnostic strategy to generate mutant from the uniform distribution of sampling mutation operators, which decreases the overall efficiency of fudging. They argue that each seed mutation strategy should be adaptively tuned for the target program and seed file format. So their adaptive strategy successfully assigned the very different probability of each mutation operator depending on the target program, like figure on the right. As you can see in these pictures, when testing PNG fix, the sampling probability of the second operator extra override is about only 1%. But when testing another program, obj dump, the sampling probability is about 22%. That is, depending on the target programs, the sampling probability of each mutation operators will be very different. And motivated from this observation, the goal of CMFudge is to also find an optimal mutation strategy for each target programs. And to achieve this, this technique is to reduce the original problem for finding an optimal strategy into solving a multi-armed bandit problem, which is one of the well-known problems in the machine learning field. And like the particle and swarm in the customized PSO algorithm of MOPT, in CMFudge, each arm represents and corresponds to each mutation operator, and the selection of arms corresponds to the selection of the mutation operators as well. And unlike MOPT, CMFudge additionally argues that we should consider seed file format as well for the effective fudging. To do so, they additionally utilize the byte stream of each seed as the low feature for running the optimal mutation strategy in the havoc stages. So personally, this paper is very similar to MOPT paper and present a very similar solution except for reflecting the seed file format of the target programs for finding optimized strategies. So I will omit the details of this CMFudge. In this experiment, the performance of CMFudge is also impressive. CMFudge used 12 popular open source programs as benchmarks and 1 day as testing budget. And CMFudge outperforms, namely PT Fudge, which is the program agnostic fudger in terms of bug finding, and unique paths. And for your interest, PT fuzz actually is a descendant of AFL. So you can consider as PT fuzz as AFL. And additionally, SAM-fuzz also compared with the previous program adaptive fuzzing technique, MOPT. According to their paper, the performance of SAM-fuzz is much better than the one of the MOPT. So as you can see this graph, in this graph, the x-axis means the testing budget and the y-axis, the number of unique paths. And as you can see, this SAM-fuzz is much better than MOPT. But personally, I'm not sure about this experiment result. This is because MOPT paper set the testing time as the 10 days, but SAM-fuzz compared performance for just 1 day. So I'm actually, personally, it's not confidence for SAM-fuzz is always effective than the MOPT. And before concluding this week lecture, I would like to discuss one interesting point, which is the ineffectiveness of determining stages. As you have already noticed, state-of-the-art techniques such as MOPT and SAM-fuzz mainly focused on finding optimal mutation strategy in havoc stage, not determining stick stages. So if using AFL a little bit seriously, there exists the fact that most people are probably noticing. The fact is that when testing real-world program having the more than millions lines code, the deterministic stage very often contribute to reducing the overall effectiveness of fuzzings. So for that reason, MOPT also employed a very specific heuristic, namely pacemaker, that selectively skips this deterministic stage under the certain criteria. So at the initial stage of MOPT, this technique also generates mutant based on both stage, deterministic stage, and havoc stages, like AFL. However, if failing to generate interesting mutant for a given time budget produced by the users, pacemakers start to turn off. Once the pacemaker turns off, MOPT generate a mutant only in havoc stage because this author also already know about the ineffectiveness of determining stages. Okay, let's remind the experiment result for AFL and MOPT shown in the previous slide. MOPT was overwhelmingly more effective than AFL. But to me, this experiment result seems to be unfair. This is because only MOPT skip the determining stages using the pacemaking heuristics, while the baseline AFL always conduct deterministic stages. So I was curious personally, and both of them performed an additional experiment with a setting that skips determining stages. So what do you think the result will be? Do you think MOPT will overwhelmingly beat AFL when AFL also skip the determining stages? So what do you think about this? The results were quite surprised to me. MOPT was only slightly more effective than AFL in terms of the number of unique paths. As you can see, this graph, the x-axis means represent the testing budget, which is hour, and the y-axis, the number of unique paths. And as you can see, MOPT is very slightly better than AFL when skipping the determining stage for the AFL. So anyway, so based on my personal experience, the inefficiency of deterministic state is very crystal clear when testing real-world programs. So if you are interested in mutation-based fudging, consider skipping this deterministic stage. Okay, let's sum up these lectures. So today we have learned about the recent trend of the mutation-based fudging, which is program adaptive fudging. And in particular, we only explore the program adaptive seed mutation strategy, such as MOPT and CM fudges. And also we discussed about the ineffectiveness of the deterministic stages. Okay, this is the end of this lecture. So see you next week. Goodbye, everyone.